Good afternoon, everyone. My name is Syed Raqueed Bin Alvee. I'm currently pursuing my master's at Texas A&M University, Kingsville, and I'm working under Dr. Kim. Today, I'll present our work, ransomware attack modeling and AI-based ransomware detection for digital substations. And after that, we have the outline. These are the topics that I will be covering today for our presentation. The introduction will include a brief summary of ransomwares and the history of ransomwares. And after that, we have the ransomware attack modeling for a digital substation. Then we have the proposed ransomware detection method. And following that is the validation and the conclusion. Now let's start with the introduction. So ransomware is a type of malware from cryptovirology that threatens to publish the victim's personal data or purposely block access to it unless the ransom is paid. While some simple ransomware may lock the system so that it's not difficult for a knowledgeable person to reverse it, more advanced malwares uses a technique called cryptoviral extortion. It encrypts the victim's files, making them inaccessible, and demands a ransom payment to decrypt them. In a properly implemented cryptoviral extortion attack, recovering the files without the decryption key is an intraceable problem, and difficult to trace. Digital currencies such as PaySafeCard or Bitcoin and other cryptocurrencies that are used for ransoms make tracing and prosecuting the perpetrators difficult. Um, Coming to the history of ransomware attacks, CryptoLocker was particularly successful, procuring an estimated $3 million before it was taken down by the authorities. And in 2015, ransomware attacks became a global concern after more than 14 million Kaspersky users were attacked across different sectors. After that, there were 181.5 million ransomware attacks in the first 6 months of 2018. This record marks a 229% increase over the same time frame in 2017. The WannaCry ransomware was a worldwide cyber attack in May of 2017 by the WannaCry ransomware cryptoworm, which targeted computers running the Microsoft Windows operating system by encrypting data and demanding ransoms payment in Bitcoin and cryptocurrency. The attack was estimated to have affected more than 200,000 computers across 150 countries, with total damages ranging from hundreds to millions to billions of dollars. Then we have the ICS ransomware. Recently, we can see that there's a trend that ransomwares are attacking industrial control systems more than ever. And it increased about 500% from 2018 to 2020. Recently, the Colonial Pipeline attacks was one of the biggest cyber attacks that has ever taken place in the United States. Hackers gained entry into the networks of the Colonial Pipeline Company on April 29th through a virtual private network account, which allowed employees to remotely access the company's computer network. And Colonial paid the hackers who were an affiliate of a cybercrime group known as DarkSide 4.4 million ransom shortly after the hack. The hackers also stole nearly 100 gigabytes of data from the Colonial pipeline and threatened to leak it if the ransom wasn't paid. And here we see the two basic ransomware detection methods, which are the static analysis and the dynamic analysis. The static malware analysis examines the ransomware without executing the actual binary files. But on the other hand, the dynamic analysis detects ransomware attacks using abnormal behavioral data caused by the compiled ransomware or ransomware events by adversaries in the target system. And simple static analysis methods utilize static data such as header information, file hash, and URL. And Static analysis has some limitations due to the packed nature of the malware. On the other hand, the accuracy of the dynamic malware analysis is not efficient due to the intelligent behavior of the malwares. Coming to digital substation and attack vectors, as we all know, the digital substation is a term applied to electrical substations where operation is managed between distributed intelligent electronic devices, IEDs, interconnected by communication networks, compared to conventional substation. A digital substation has much more smart devices, and this allows for a greater surface area for an attack because of because there are so many smart devices which are hackable and which can be penetrated by attackers. So this leaves a good surface area for the hackers. The figure that we see has three potential ransomware attack vectors targeting to disrupt a substation control and diagnosis unit operation in a local substation control room. An attacker's goal is to encrypt the CSDU local system by ransomware attack vector 1, which is the attack vector 1 is an external network attack path initiated from the platform information technology, the PIT, involving vendor access servers, diagnosis centers, control centers, and other remote access points. The attack vector 2 is a local attack route started from the internal substation in the operation technology, OT. The attack vector 3 is a physical intrusion, and intrusion detection system activated DMZ is established between the PIT and the OT networks. The ID implements a deep packet inspection and ransomware detection programs against all incoming ransomwares from the PIT network. And for the ransomware attack model, we have different choices, but we chose to go with the one that was used for the colonial pipeline attack because it was more relevant and more recent. The figure above shows a kill chain ransomware attack model for digital substation having 12 ransomware attack phases. The attack scenario has been created by referring to colonial pipeline ransomware attack incident reports, and an advanced persistent threat APT actor is accessed a PIT system by social engineering or by exploiting remote accounts leaked in the dark web, and backdoor malware established then executed in the system. And after that, the adversary is continuously maintaining a foothold until a remote valid using a valid remote desktop protocol. And after getting an access token and gathering substation data, the APT actor can access the on-site SDU system with the field network authority, including all connected local devices. By encrypting the response function, control process, and the security alarm related programs, the SDU controller is disabled to use, and the APT group demands the substation operator to pay a ransom with an additional threat to disclose collect the substation data and system weakness information on the dark web. Now we come to our proposed method, and the algorithm that was used in our proposed method is a CNN, which is a very famous deep learning algorithm, and we used it to train it with the grayscale images that we extracted from the binary ransomware and the goodware files. And this figure illustrates the proposed algorithm and how it uses the image as an input to detect ransomware files. And the design of the ransomware detect method consists of three sequential processes: the data pre-processing, the feature learning from the image, and the classification. And now we come to the data pre-processing. First, an executable ransomware or goodware file is converted to a vector form by reading unsigned 8-bit integers. A 2D array is then created based on the size of the binary file, and table 1 shows the recommended image width according to the file size. So after the matrix is formed. Each value in the matrix is assigned in grayscale colors ranging from 0 to 255. And after that, the 1D grayscale array is converted to a 2D grayscale matrix, and then it's finally converted to a 2D grayscale image. And after that, we come to the part of the data augmentation. Since unbalanced data sets are a common problem in computer vision and image classification problems, the lack of images in each layer can lead to underfitting and overfitting, which has a big impact on the CNN for performance. Therefore, a data augmentation method is provided in the ransomware data set to improve the performance of the classifier. The data augmentation is a method used to enhance a data set commonly used to train neural networks. To further improve the attack detection rates within a limited number of ransomware samples, common pre-processing techniques such as rescaling and sample-wise standardization are also applied. The design of these the CNN model architecture has a multi-layered structure consisting of 2 convolutional layers, 2 max pooling layers, 2 fully connected layers, and softmax. ReLU is chosen as the activation function, and it does not change the size of the image, and the ReLU is good for increasing nonlinearity from the images which have high nonlinearity. The noise impact of the features is reduced by the pooling layers. To fully connected layers utilizes the output from the convolutional process and predicts the class of the image based on the features extracted in the previous stages. Each neuron is processed by a point element between small regions and weights related to the amount of information. Softmax is used in the layer of the CNN, which normalizes the CNN output between 1 and 0, and 1 would indicate that that it's a ransomware, and 2 would indicate that it is a goodware. And the other user configurable hyperparameters, including learning rate, number of hidden layers, number of nodes, number of epochs, stack size, and type of activation functions are optimally chosen by trial and error effort. The data set consists of 672 goodware samples and 845 ransomware samples. The ransomware files consist of 5 different families: Cerber, Tesla, Cryptlocky, and DarkSide. The goodware portable executable files are collected from the Windows platform and from the portable apps platform. The proposed CNN ransomware detection model is designed and trained in the Colab, a cloud computing platform provided by Google. The experiment is run on the Windows computer running an i7 RTX 2060, 16 gigs of RAM, and the program is written in Python 3.9.7 with Keras and PyTorch as the backend. The figure depicts the accuracy results of the training and experiments of the CNN-based detection models for 40 epochs. The accuracy values of training and validation converge to 99% and 96.22% respectively. The difference between these two accuracies is negligible. The loss curves of the training and validation converge to 0.0056 and 0.0388 respectively. This shows that the proposed method is unbiased for the training images, but it also provides high ransomware detection accuracy. These results show that the proposed CNN-based detection method is accurate and suitable for ransomware file detection. And among all machine learning classifiers, random forest method based on the n-grams of opcode shows the best accuracy. Compared to this method, our proposed method shows higher accuracy. And also in the other machine learning classifier method, they had to use a disassembler to get the opcode from the binary file. But in our proposed method, it removes the redundancy of having to use a disassembler, as it can directly extract features from the images. And after that, we have the conclusion. This paper has explored potential attack surface of ransomware attacks in a digital substation and provided a CKC-based ransomware attack model. The paper has investigated AI-based ransomware file detection methods. The CNN-based ransomware detection system can detect malware files with high accuracy without additional components such as disassembler. The future works include evaluating the proposed algorithm in the IDS in a real-time hardware-in-the-loop cybersecurity testbed for a smart substation, and also improving the detection accuracy and reducing the detection time. And here's our acknowledgement. And please let me know if you have any questions. Thank you.